implicit differentiation. You do not need to know why this is working because it's outside the scope of this module. Suppose I want to find the dy dx of this. How will you proceed it normally? You will say, okay, I need to write something y equals fx, okay? Too bad, this guy you can't. Let's say you can't. For this kind of function, you cannot write something as y equals something fx, then you cannot say dy dx and look at the expression and then dy dx. This one is hard to do. Then what? Then here's the idea. You do implicit differentiation, which you need to know a new thing called partial derivative. Not the focus of this module. I just let you know this thing exists. This is the first time you see it, so I'm now explaining what the heck is this new symbol. I now have a function more than one variable. I have fxy. So my domain is what? Cartesian product of r cross r. So this is my domain. 2 number. What's my output? 1 number. So my output is r. Partial derivative of this big F with respect to x at a point AB. Why is AB? Because now we have xy, so no longer just A. We can call it AB. I write this, we no longer write this D. This is actually have a name called total derivative. Now this is called partial. Total means everything. This means part. You may then wonder, can I take the total derivative here? Yes, you can, but not now. We now take partial derivative of this. Partial derivative means I only care about one part. Previously, I talked about differentiation is like finding a slope. Then what about this? You have a 2-dimensional surface. And now you are doing the same thing. You are standing here. You only view this particular plane and you are looking at a particular red curve across this plane. And you do this. You ignore other coordinates. So that's the idea of partial. So I'm doing this partial f partial x. So I'm derivative this guy on x. So I add h only on the x. So that means what? That means derivative means you have plus h and h go to very small, right? So now I plus h only on the x part. And what is this thing? This is exactly the epsilon delta definition of limit. But now for partial derivative. So this thing called partial derivative. This is the symbol. So if I partial f partial x, it means I do this on the x part. If I partial f partial y, means I do this on the y part. Okay, these are math language. What is the human language? Human language is you partial f partial x is just df dx ignore y. Partial f partial y is just df dy ignore x. What does it mean ignore? You treat the other part as constant. So here's an example. What's the theorem here? The theorem is saying that if I have an implicit function that fxy that I have somehow no way to write y as some fx, I just do this, the whole thing partial x and then plus the whole thing partial y and then dy dx. This actually is chain rule, but don't worry. So what I'm going to do, the whole thing partial x. So I ignore all the y, take y as constant. D this guy 2x. D this guy, y is a constant. I don't care. So it's what? Negative 1. 1 with the y, so I have a y here. D this thing, y squared is constant. So I also have negative 1. And then so I have a negative y squared. So this part on this thing is 2x, negative y, and negative y squared. You see there are some other thing, right? What's that? That thing is partial f partial y times dy dx. So first I need to know what is partial f partial y. Partial f partial y is just d this thing on y. Ignore x. So let me use other color. So now I have this. D this guy on y. This is constant from y. Nothing. Gone. 0. D this guy on y. Negative x. D this guy on y. Negative 2xy. So I have negative x and negative 2xy. Right? So this is what I have. But for all this term, I need to stick with a dy dx here. So that means everything here I need to put a y prime here. That's exactly these two guys. So the red part is what? The red part is this part. The blue part is this part. And the dy dx is I just stick to it. Okay, then I get this. Then what's next? Once I get this line, I just simplify the expression. What is the goal? The goal is to find dy dx. So I just need to try to write this thing as my main character. Okay, so what's the main character here? Dy dx. So what I'm going to do here is this thing. I simplify stuff. So this thing have what? Y prime. This thing have y prime. I group them here and I throw everything else to there. So 2x go to here, this guy go to here, and this guy go to there. Notice that this is negative, so it's the same as these two guys go to the other side. Okay, so I get this. Now what? These two terms both have y prime. So this term is the same as x plus 2xy. Y prime is dy dx, right? Now I throw everything to the other side. So here. So therefore, that means what? This function, if you want to find dy dx, you cannot do it normally. You have to do implicit differentiation. And the answer is this. Why? I introduced a new concept called partial derivative. You don't need to know what is this. You technically know it next semester. Basically means what? You only d one part of the function. You ignore the other part. Okay? This is called partial derivative. And because this is something out of scope, so you actually don't need to know this. I just let you know this thing exists. Okay? And this is another example. For example, okay, this is a powerful example showing that why this is important. How do you find dy dx this guy? You can't even do that because this y is inside cosine function. Okay? How will you approach this? Technically you can't. But if you really want to do that, okay, I would say then you first do Taylor series, expand this, then you have infinite number of y, and then you take dy dx on each term and then try to group them. That will be a mess. But if you do implicit function, this is expression. Now you see dy dx, this no human can come up with this by just looking at the formula.